All right, welcome back to another calculus lecture. In today's lecture, we're going to talk about the second derivative. So up to this point, we've really just been dealing with the first derivative of a function. So I differentiate a function, and then I use it for solving this, that, and the other problems. But really, there's no reason why we can't say, okay, well, I have the derivative, and then let's compute the derivative of the derivative. And this is the second derivative of a function. Also, real quick, I'm recording this lecture at about 11 o'clock on June 2nd, and people treat 4th of July as a multi-day holiday, so if you hear fireworks outside, sorry for the bad video quality. Oh well. Anyway, so the second derivative. Well, what is the second derivative? Definition. The second derivative f double prime, so we just do with the Newton notation, we do a 2 primes instead of 1, f double prime of x of f of x. So the second derivative of f of x is the derivative d dx of f prime of x. So I simply differentiate the first derivative of the function. And you might think, well, we can actually just continue this process. We can do the third, the fourth, the fifth, however many derivatives you want. We'll really just deal with the first and second derivatives in this class. If you want to learn more about higher derivatives, that sort of requires more exploration in other calculus classes, namely Calc 2 and 3 will deal with that sort of thing. Not exclusively, but it's a topic you would cover there. So the second derivative is simply the derivative of the derivative. And one thing that we might ask is, maybe we'll pose this as a question, what does the second derivative represent? So we know that the first derivative represents rate of change. It represents, if I have a position function and I compute its derivative, then I get a velocity function. I get the rate of change of position. But what exactly does the second derivative represent? Well, the answer is that f double prime of x, the second derivative, represents the rate at which the derivative, the first derivative, is itself changing. So one of the really neat things about calculus is you can start talking about these very complex situations where I have a rate of change, and that rate of change is itself changing with respect to time. We've seen many examples of this. When I differentiate a function and I don't just get a number, well, that means that the rate of change of the function is itself changing with respect to whatever my independent variable is, and the second derivative allows us to measure that rate of change that the rate of change itself is changing at. This gets very linguistically difficult after a while, but I assure you it is actually valuable to talk about this. So maybe as an example, if s of t represents position at time t, then s prime of t represents the rate of change of position. That is, it represents velocity at time t. Or we'll just say represents velocity. And then what is the rate of change of velocity? Well, if you think about if you're driving in a car and you're trying to increase your speed, what do? You accelerate. And so the second derivative represents acceleration. And s double prime of t represents acceleration. I believe the third derivative represents something called a jolt, which is the rate of change of acceleration, which once you get to the point of actually worrying about that, you're off into physics land, and we're not quite going to get there in this course because this is calculus and not physics. But anyway, so this is how we can think about the second derivative, at least from a physical perspective. This is what the second derivative represents. It is the rate of change of the rate of change. It is the rate at which the rate of change of the function is itself changing. Okay. Again, this gets linguistically confusing very quickly if we go into higher derivatives, so we'll just content ourselves with this for the moment. So maybe let's just do an example of this. Let's compute a second derivative. So example, compute f double prime of x if f of x is equal to, oh, I don't know, x squared plus cosine of x. Okay, so I have this function. It's something. I don't know exactly what its graph looks like, but it's a function, and I can compute its derivative certainly. So f prime of x is equal to, well, let's differentiate this. I get 2x minus sine of x. So I apply the power rule, and then I apply my trigonometric derivative. So here's my first derivative, and now to compute the second derivative, I simply differentiate this. So f double prime of x is equal to, let's look at this, the derivative of 2x is just 2, and the derivative of sine of x is cosine of x. Interesting that we've gotten actually back to cosine of x, but we've picked up a negative sign. This happens when you differentiate trigonometric functions multiple times. But yeah, if you just want to compute a second derivative, you simply just do a derivative, but do it twice. Okay, simple as that. And in your homework, you'll have a few examples, and in the quizzes, you'll have a few examples of computing first and second derivatives. Okay, so this is how we can think about the second derivative and compute it. But maybe another question to ask, and kind of in the same vein of what we've been looking at in the past couple of lectures, is what does the second derivative represent graphically? So we'll go ahead and write that down. What does f double prime of x represent graphically? Well, we can ask a couple of questions here. So with the first derivative, we know that if the first derivative is positive, then my function is increasing, and if it's negative, my function is decreasing. We saw that a couple of lectures ago. And then in the last lecture, we saw that if the derivative is 0, then I'm at a local extrema. Well, we can ask the same pair of questions about the second derivative. So what does the sine of the second derivative represent, and what do the zeros of the second derivative represent? So what do the sine and zeros of f of x represent? Okay, so maybe I'll write out a sort of theorem, and then we'll go into some mathematics software and actually graphically look at this. So before we look graphically at what this is, maybe let's give a definition, or actually the definition is really just going to be some pictures. We could give a formal, rigorous definition in symbols only, but I think it's more helpful to just sort of see the picture. So definition: the concavity of a graph is defined as follows. And I'm really just going to define it with a couple of pictures. Again, we could give a rigorous definition like we did for increasing and decreasing, but it's a little bit more sort of technical, and I don't want to take too much time to go into it when really the picture is sort of adequate for understanding this. So let's get a axis in here. So a graph which is concave up simply looks like this. This is concave up. And a graph that is concave down looks like this. You can think of concavity as the way the graph opens. So maybe I'll write that concavity is sort of the direction the graph opens. And that's a very non-rigorous definition, and if some mathematicians watching would be very upset if I sort of just leave it at that, but I am, because I think really the pictures do a pretty good job of describing this. Really what's going on is the tangent line to the graph is sitting either below or above the graph at a particular point. But you can think about concave up and concave down as the direction that the graph is opening. So if it's opening upwards, then I have a concave up graph, and if it's opening downwards, then I have a concave down graph. Okay, and if I draw maybe a tangent line in here, then you can see what I was saying. The tangent line is completely below the graph, and if you're concave up, then you are completely above the graph. So that's the rigorous definition, but really graphically this is what's happening and what I really want us to understand. So this begs the question, well, I've just introduced this concept of concavity, so how does that relate to the second derivative? So let's go ahead and write that down as a theorem. So if f double prime of a is greater than 0, so if the sign of the second derivative is positive, then the graph of f of x is concave up at x equals a. And if f double prime of a is negative, then, as you would expect, the graph is concave down. Okay, so this is the relationship between the second derivative and the shape of a graph. So whereas the first derivative represents increasing versus decreasing, the second derivative tells us about the concavity of a graph. And this is somewhat abstract, so maybe let's go into Mathematica and see a picture of this. Yeah. So here I've got just a function that's graphed, and I've got 3 points marked on here. So I've got a local maximum marked here, a local minimum marked here, and then this other point that I'll talk about in a moment. And I don't think this is actually capturing my my mouse. So we're gonna pause that there. Okay, so let's pop into Mathematica and actually see an example of this and kind of how this is working out. So in here I've got this function that is just being plotted, and I've got a few special points sort of marked on the graph. So I have this local maximum marked here, and I have a local minimum marked here, and then I have this other point, which I'll talk about in a moment, marked here. So this is the graph of the function. I'm going to overlay the graph of its derivative on top of it. So that's what this is. The yellow line here is the derivative of this function. And notice that the zeros of the derivative, that is where the derivative is crossing the x-axis, correspond exactly to where I have a local maximum and a local minimum. That's what our lecture yesterday talked about, is that the critical points, that is the zeros of the derivative or the points where it's undefined, these are the points where the graph can potentially have a local max or a local minimum. Okay? And so here's the graph of the first derivative. Now I'm going to overlay on top of this picture the graph of the second derivative. So this is going to be the green function. So the green function here, notice that its 0 corresponds to this point right here. And also notice that when the derivative is positive, or when the second derivative is positive, that is, I am above the x-axis being this black line right here. If I'm above that point, then my graph is concave up. It's sort of opening upwards. And likewise, if I'm negative, so I'm to the left of 2 here, then my graph is concave down. It's opening downwards. And so you can see that the second derivative corresponds to these points where the concavity potentially switches. And the points at which the concavity switches are called inflection points. And we'll write that down as a definition in a moment. Notice also that the derivative, or the function, is increasing up to this point, and the derivative is positive. It's above the x-axis, and then it goes below the x-axis because the function starts to decrease. And then again, we switch to being above the x-axis because the function is increasing. Okay? So this is how the first and second derivative are sort of related to the graph of a function. They tell you all of this information about concavity, about increasing versus decreasing, extrema, inflection points. All of this is available via just the first and second derivative. So going back to the notes here, let's go ahead and write down that definition that I said. So definition. So if the concavity of the graph of f of x switches at x equals a, that is, it's concave up on one side and concave down on the other, or vice versa, then a is called an inflection point. And we should note that just because the second derivative is 0, that does not mean that you have an inflection point. It is certainly possible to have a second derivative that is 0, but you do not have an inflection point. So note, or note of caution, f double prime of a equals 0 does not mean that a is an inflection point. However, golly, the converse is true. That is, if I have an inflection point, then my second derivative is 0. So theorem, if x equals a is an inflection point, then the second derivative is 0 at that point. And so just in the same way as the critical points give us the candidates for the local maximum and local minimum, or local maxima and local minima of the graph, so too the second derivative zeros give us the candidates for inflection points. Those points don't necessarily have to be inflection points, but they are at least candidates for being inflection points, because if I'm at an inflection point, then the second derivative is going to be 0. Okay? So maybe let's just do a quick example of this, of why this happens to be the case. Consider f of x equals x to the, actually we'll just do x squared. Okay? No, I don't want to do x squared. So let's do x to the 4th. Then f prime of x is equal to 4x cubed, and f double prime of x is equal to 12x squared, just applying the power rule twice from here to here. And notice that the second derivative is 0 when x is equal to 0. Thus x equals 0 is a root of f double prime of x. So we have the second derivative is 0 at the origin, at x equals 0. But the graph of f of x is, and the graph of f of x looks something like this. Looks kind of like a parabola. Notice that at x equals 0, I don't have an inflection point. The inflection does not change at all at the point 0, even though the second derivative is 0 at that point. Okay, so just because your second derivative is 0 does not mean you're at an inflection point, but if you are at an inflection point, then your second derivative is 0. So you have to be careful about the implication there, just like we did with the critical points. Okay, so that's pretty much everything I wanted to talk about in this lecture in terms of what the second derivative is and what it represents. In the next lecture, we'll talk about how to use the first and second derivative to classify the extrema of a graph, and we'll specifically look at the first and second derivative tests. Okay, so see you all in the next lecture.